Today I'm going to introduce to you Dr. Young, who is CEO and co-founder of Shannon Systems, where he led the development and commercialization of enterprise-grade PCIe SSDs. They're industry leaders in storage capacity and scalability, ultra-low latency, and low power. They have a low-power envelope. The SSDs developed under his leadership include a 12.8 terabyte PCIe SSD. Before co-founding Shannon Systems, Dr. Young was the chief architect at Marvell, where he designed its first generations of SSD controllers. He's also been a research staff member at Seagate and a postdoctoral researcher at Princeton University. He earned a PhD in electrical engineering EE from Drexel University in Philadelphia and a BSEE from Tsinghua University in China. Dr. Young holds over 100 US patents, granted or pending, and we're looking forward to his presentation. Thank you very much. We're going to welcome Dr. Young. Thank you very much.
Thank you. Good morning, everyone. Thanks for the introduction. And so it's my great pleasure to be here to introduce you some of the most recent advances in open channel SSD that we are making here at Shannon Systems. So many of you might not be familiar with Shannon Systems. I will just make a brief intro before I start with the presentation. Okay, Shannon is an enterprise SSD solution provider based out in China, Shanghai, China. Okay, the company was founded in 2011 and by a group of people from the Silicon Valley. And in 2015, Shannon, we became a wholly owned subsidiary of Silicon Motion Technology Group. And we provide SSD solutions to over 80% of the Chinese internet companies, as well as enterprise customers, hundreds of enterprise customers. We are one of the largest independent enterprise SSD solution provider based in China. With that, so today it's my great honor to be here with some of you, the most distinguished industry expert, to share with you the progress we made on open channel SSDs. Okay, to make your time spent here really worthwhile, we are also going to make an important product launch and announcement here. So, which, by the way, is the industry first in terms of time to market. Okay, so stay tuned, stay put. So today, essentially, we are going to answer 3 questions. Why open channel SSD? Why open channel SSD is needed? And then how open channel SSD is different from conventional SSDs. What is the key differences? And how we are going to make that. Okay, and then finally, the third question is what progress we have made, and what's the implications, or what's the advances for that. Okay, so let's take a step back and see what really SSDs brings on the table for everyone. In fact, from an SSD, in general, a storage device perspective, everything can be described as a transaction. Okay, the human society started from the very beginning. I'm sorry, I apologize. This is automatically flipping the page. There's a transaction in the history is that people travel from place to place and make the trade. But today, obviously, the transactions is vastly different. So this is the warehouse of Amazon. Okay, the robots carrying all the goods from one place to another, trying to fill the individual orders so that the shipment can be carried out in a fast version. So that's the transactions of today's warehouse. So, okay, so basically the transactions can be described in 3 characteristics, so-called 3 V's: the volume, the velocity, and the variety. So let's focus on the first one. So what's the the volume. So this is the number that is representing the number of tickets sold for the high-speed rail in China. In 2007, the number of tickets sold per year is 1.5 billion, but so to 3.5 billion. Okay, that's the sheer amount of volume that we talk about here. In terms of velocity, this is a classic example of transaction velocity. Last year, in Alibaba's Singles Day event, the number of transactions happened in the first 3 minutes. The GMV, or the gross market value, the gross merchandise value, passed $1.5 billion US dollars. In terms of variety, there's an app in China called Tantan. Okay, so that's similar to Tinder in the US. So when you like someone, you find someone you like, you swipe to the right, and if the other person also likes you, it will be a match. That's 900 million swipes a day. That's last year's number. Okay, so think about that's average in person in China, there's going to be one person make a single swipe every day. I'm sure that my swipe was, done by someone else, my average swipe. Okay, so that's the 3 V's. And so basically everything happens. It's going to put a tremendous amount of pressure on the the data center infrastructure, because everything happens is going to be create a transaction, right? So people has been asking for basically 2 things: higher quality of service, and at the same time, lower cost, total cost of ownership. That's it. That's basically the 2 things. So what the traditional SSD has been done in a great deal to improve the quality of service, also lowering the cost of ownership by reducing the cost of NAND. So, so how are we going to do better? How are we going to do better with open channel than the conventional SSDs? Right? So let's start with the traditional SSD model, where the application, how the application accesses the NAND. It starts with a middleware underneath it, and databases. That's in the user space. Okay, this is a typical application. And then the virtual file system, the actual file system, XFS or ex4, and so on and so forth, block layer, and NVMe driver. So that's on the kernel space. So finally, comes the hardware. That's going to be FTL. So many layers of all the, from the application to the NAND. So there's significant detour of, the data running from the NAND to the application. So that's the so-called agent problem. Why is the agent problem? This is the agent from the matrix. Of course, agent from matrix, they have the artificial intelligence, is highly intelligent. But in reality, what we are facing here is all the agents sitting between the application and the NAND, causing a lot of problems, in particular for SSD applications, because SSD is so much different from a conventional storage device, which is HDD. Okay, so what Open Channel SSD has done is that reducing the agents from the application to the NAND. It just becomes a single layer. That's the I/O and flash management. We call the I/O and flash management layer. So the applications talk to the NAND basically via APIs tailored to the application. For example, if it's a key value store, so the I/O and flash management module will provide a specific key value access APIs for the application. And the application also going to send data hints to the I/O managers. On the other hand, the NAND status hints, whether it's busy or not, how many cycles it has endurance, what's the error statistics of the current NAND module. So all these data hints going to send to the application. So that's we call reducing the agents from the conventional SSD model that being accessed by the application. So go one step further. We are going to completely eliminate the agents. This is made possible by the open channel SSD architecture. So the application actually becomes part of the I/O manager or flash management. And from another perspective, the open channel SSD becomes part of the application. So the application going to be adjusting the NAND in terms of physical block devices, physical block address, in terms of channels, chip enables, and blocks and pages, and so on and so forth. It's so much different from the conventional logical space address method. So this is the most efficient way to address the NAND, or to passing the data from the NAND to the application, or store the data from the application to a NAND. So the open channel SSD can be actually classified in two modes. One so-called kernel mode, which is described here. So again, we have a typical model. There's a user, kernel, and hardware. So the I/O engine on the flash manager will be sitting in the kernel space. So for example, the I/O engine, we have block device or namespace or key value and so on. Underneath that, there is a very thin layer for light NVMe driver. That's basically translating the commands to the hardware, talking to the PCIe link, for example. Okay, so underneath the hardware, there is going to be a controller logic talking to the NAND that is correcting all the errors, the random errors, and so on and so forth, doing the repetitive task, the mundane task of correcting the errors. That's all. So in this kernel mode, the engine and the I/O manager becomes part of a driver. Okay. So there is another second mode we call the user mode. So the I/O engine actually and the flash manager sits on the application space. It's no longer in the kernel space. This is where it creates a lot of flexibility because first of all, it can, for example, avoid the so-called interrupts overhead. Also, it can be part of the application. Okay, so in this case, we see a lot of performance improvement compared to the kernel space because there are limitations what it can do in the kernel. In the user space, it's more flexible. So these two modes essentially creates the open channel SSD architecture. So one key message I want to share with you here is that open channel SSD essentially becomes part of the application. It's no longer independent or third party from the application's perspective. So lastly, the most important thing I want to share with you today is what has been done on the open channel SSDs, what progress we have made, what kind of results that we have obtained so far. Today, I'm very happy to introduce you the open channel SSD platform we codenamed Venice. The Venice is an open platform to support various requirements for open channel SSD implementations. It consists of a hardware silicon, the SoC, which is a 16 NAND channel controller. It's 8-LAN PCIe Gen 3, It comes with a standard 6-core ARM cores. Okay? It supports QoS, TLC, NAND. So one thing I would, it comes with both user and kernel space support implementation with a complete software stack. So this includes, of course, but not limited to, direct NAND addressing, polling, status polling, and a completely user-defined flash management. One thing that I would like to highlight is that our unique pluggable module framework that allows users to rapidly assemble and customize its own open channel open channel SSD requirements into under the open channel SSD framework. So it's a pluggable module framework that you can put pieces together. So on this platform, we have been working very closely with Alibaba in the last 2 years. We've been started working in 2016, and we have made a tremendous amount of progress to date. And Alibaba has its own unique requirements on SSD needs, obviously. There's significant volume of transaction and business varieties. And also, it's completely a transaction-oriented business, requires vastly different IT infrastructure from other hyperscale data center players. So Alibaba defined its own open channel SSD spec, so-called Alibaba Open Channel SSD, AOC, codenamed. So we are very happy to announce today that this close development has been in production today. So next, I'm going to introduce some of the flavors of open channel SSDs. Okay, what's the functionality of open channel SSD, to be more specific? So the first one I'm going to share with you is the quality of service provisioning. So here is a graph showing the application of that. So underneath the bottom is open channel SSD with OCS I/O engine. So it's going to provide volumes to the application. So for example, you have 4 instances, 0, 1, 3, 4. Obviously, there's a 2 missing here. So, so you can specify, for each volume, you can specify whether it's high priority or normal priority, or even has different levels of priority if you need. Also, you can specify the number of IOPS that it can be, it is allowed, so that in cases that many instances share the same SSD resource, I/O resource, some of the application will not stop. Right? So with this prioritization of I/O and also quality of service guarantee, it provides a perfect environment for the cloud application, cloud computing application, because in most cases, there are many users are sharing the same SSD resource. In some cases, we see hundreds of user instances sharing the same I/O resource. So it's very important to make sure that each user is allocated the proper I/O priority as well as quality of service. So this is one example that's showing when you have different priorities for the I/O. The red one representing the so-called normal I/O priority. Okay, the blue one is the high priority I/O. So the y-axis is the latency. We can see that when you specify the I/O to be a high prioritized ones, you see almost 1 order of magnitude improvement or reduction in terms of latency. This is very important for many applications. For example, when you have a log for a database application, you want because that's the bottleneck of the application. So you want that traffic to be prioritized. So you specify that with a volume, with high priority, so that it can be served in front of other traffic. So in this case, you will see a tremendous boost for the application. Next one is so-called thin provisioning. As we all know, thin provisioning is such a standard feature for storage system. But when you have an open channel SSD, you can make that happen from a device level. So this is a 4 terabyte SSDs. Physically, the physical space is 4 terabyte. But we can provision the service to over 100 instances. Each instance, appear to the instance, there's going to be 4 terabyte space for each instance. So the open channel, we are taking care of the over provisioning, the same provisioning, and alerts the application when it's real, there is a running out of physical space. And so at that time, the user can decide whether to migrate the data to another volume or not. So this essentially puts the device much smarter than the conventional device, SSD device. It becomes a mini storage system. So the next feature that I'm going to share with you is so-called atomic writes. Okay? This is very useful for database application. Many of you know that in order to guarantee the data integrity in database application, the data, especially the bin log data, has to be written twice to the media. So when you have atomic writes, the data is actually only need to be written once instead of twice. So in this case, for the OCS, what we have done is that we are going to put atomic guarantee in the driver, or in the, in this case, I showing here is an example on the kernel mode that we put the atomicity in the kernel space. So it works for any file system. I want to highlight that. There are some providers that they have to use their own file system in order to guarantee the atomicity of the writes. But here, we can support any file system. So the application send the atomicity hints to the open channel as OCS. And with that hint, the I/O's atomicity is properly taken care of. So we have been working with the open source leader in database, the MariaDB Foundation, for a couple of years already. And since version 10.2, it provides the native support for atomic writes. So here is one example that provided by MariaDB. So again, this is a transaction per second on the y-axis, and the axis is the number of threads. Okay, the blue curve on the bottom is conventional SSDs. So when you enable the atomic writes feature in MariaDB, just a switch, the transaction per second can be increased up to almost 50%. Needless to say that it's also going to help with the latency reduction. Also, the quality of service in terms of consistency of the transaction per second is greatly improved. So with that, the open channel, the OCS, going to provide a lot of benefits to the database application users. The final topic that I want to introduce to you today is for NoSQL application. We see cloud application, we see SQL application, database, and the last one is NoSQL. There are a lot of NoSQL applications running today on the internet, being it key value, being it other, NoSQL application. So here, basically, it's very simple diagram, similar to what we described before. In this example, we provide a user space mode that provides key value access for the application directly without involving any file systems. So why it benefit? Think about a conventional key value access method. On the left, that's the conventional key value store. You have RocksDB or LevelDB. It has its own journal and compaction, right? Underneath that, that's going to be a file system with its own journal. This journal creates overhead, obviously, writes additional data, causing additional latency. And finally, inside the SSDs, you have, FTL that has its own journal, or we call it, in SSDs terminology, we call it garbage collection. So all these different layers, we call it agents, going to create so much overhead, the write amplification can be 10x to the host writes. So what we can do in the OCS model framework is that we combine this thing, consolidate it, not combine, consolidate it, eliminating the unnecessary journaling, because we know the journaling is automatically embedded in the file, in the NAND flash writes. So this creates a very simple and a powerful access for the NoSQL application. In this example, we provide a customized open channel KoS engine. The journal itself becomes a typical GC, or garbage collection. So we will see the results. When you implement this, what you're going to see, this is a very typical situation when you have 8K key value. The value size is 8 kilobytes. When you do a read, that's a get a key from the database. What we see is almost, again, 700%. When you put a key, that's a write, corresponding to a write. You see 15 times improvement. This is a breakthrough performance. And we see, actually, with smaller value size, which is a more typical application, in typical application environment, we see even 2 orders of magnitude improvement. 2 orders. So I'm very happy to announce today that we have been working with Baidu in China. So this is basically the key value SSD that is in development. And we see always similar results that we show in the previous plot. Okay, 1 order of magnitude improvement in real applications. So with that, I think I apologize for the technical difficulties. And but again, I think I want to leave you with that, with key takeaways. So Open Channel SSD has arrived. It's here. It's going to stay. And it's going to be the next generation of how you access the NAND. The conventional SSD will stay. It has its own space. But Open Channel OCS provides much more potential, bringing in further value to the application. people always ask our NAND guys to provide cheaper one, cheaper NAND, better endurance, but it has its own physical limits. What we can do is cut all the overhead, cut all the agents sitting between the application and the NAND, bring the extra value to the application, to the end user, to the customer. So that's the way to do that, obviously, is enable the application to directly manage the NAND, cutting out all the middlemen, cutting out all the agents. So that implies the open channel OCS becomes part of the application. When you do that, the OCS is going to offer significant opportunities for quality of service improvement, especially for data center applications, where the applications or storage are virtualized, are shared, the resources are shared. In this example, it provides extra value. So we explained three things, three working environment or applications for OCS, for the cloud, for SQL application, and for NoSQL application. There is much more. There is much more. We are going to share it with you as we come along, with moving forward. Okay, with that, I'm going to close my application. I intentionally run out of time because I don't want you to ask questions. Sorry. So if you want to know more about OCS, come to talk to us. We are at Exhibit Hall 219. It's easy to find, just next to the food and drink stand. It's very easy to find. Thank you.